Hello everybody, welcome back to another video, and in this video we'll be looking at the proof for the summation rule, summation angle identity for the sine and cosine functions using complex numbers. So what do I mean by that? So whenever we have some sine of a plus b, how do we figure out what those are just in terms of regular trigonometric functions of single angles without any sums? So that would be useful in many cases. So for instance, taking the limit of sine using the definition of the derivative, you will need to use the summation rule because you'll end up with the sine of x plus h. So let's try and figure this out. So we have the sine of, let's say we have a plus b, we're going to call our angles, and let's figure that out. So what we need to do is we need to use Euler's identity. So this is our want, and here we know that e to the I theta is cosine of theta plus I times sine of theta. And there's, of course, really cool proofs of this using Taylor series expansions and integrals even. So now let's actually use this, because what we see is that theta right here is our input angle. So we can put whatever we want into e to the I theta, and then that will become the input for the sine and cosine functions. So let's say now our angle theta is a plus b, because that's exactly what we're trying to find out. So our angle here is our a plus b. So let's say now we have e to the ia plus b. Then, of course, that's going to equal, then using Euler's identity, that's going to equal to the cosine of a plus b. So I'll write it like this, plus I sine of a plus b. So I'll just put it in this like so. So this. So from here, where do we go? Well, what we can see is that we can also expand the I times a plus b, because we know that this is in a bracket, so we can multiply the I to each term in the bracket. So what we see is that e to the I and then a, and then we have plus I times b. So we have an I times a b here. That is going to be equal to the cosine, or exactly what is here, because this is the exact same thing, except we've just expanded the bracket. So we can just take this expression and put it right here. However, how do we isolate for cosine and cosine? What we can see here is we actually, let's refer to a simpler example. We know that x to the power of 1 times x to the power of 2 is equal to x to the power of 3. But how do we know that? Well, we have an x to the power of 1 and 2. So we can write here, because x to the power of 1 times x to the power of 2 is equal to x to the power of 1 plus 2. We add the exponents. So what we can actually do is take the reverse. So we also know that x to the power of 3 is x to the power of 1 times x to the power of 2, because 1 plus 2 is equal to 3. So we use the exact same concept here. Instead, it's with the base e. So what we see is that this is also equal to e to the I, and then what we see here is an a, and then multiplied by e to the ib. E to the ib, because here we've just used this exact property here. So that was just a bit of a deep or lengthy explanation, but now that we have had that out of the way, we can go on with solving this. So we have this exact same expression here. However, where do we go from here? So what we see is that we know that Euler's identity is in the form of e to the I theta, and here we have e to the ia and e to the ib. Well, those each look like they could be in the form to use Euler's formula, because we have an e to the I something in both e exponents. So what we can do here is we can break these apart and see those each as their own Euler expansions. I can call it like so. So this is also equal to, now let's look at this first part. So let's say our first part right here is in this color. So what we have here is we have the cosine of a plus I sine a, and that's being multiplied by everything, but with b as the input. So let's put all of this in a bracket here, and let's use this. So we have multiplied by cosine of b now plus I sine of b. So actually, all we need to do is we see that these are now in exactly what we want. The angle is a single value. So what we can do is we can just multiply these out and see where we go from there. So let's just multiply this out. So this is equal to, and then taking this times that, that's equal to cosine, so that's cosine A times cosine B. Then we take this next part right here. We have I sine A, so plus I sine A, and then times cosine of B. And then we take this times this. So what we need to see here to do that is, so first of all, I forgot to do this. So what we see here, before we do that, we see that we have to take cosine of A times I sine of B. So that's a plus now cosine of A, and then we have an I sine of B. So let's put that I before this. So here we have an I, and then we have a sine B. And what we can now do is the final part where we now add. And then what we see here is that what we know is that I by definition is the square root of -1. So then just squaring both sides, we see that I squared is also -1. So what we see here is that when we multiply I sine A by I sine B, we have to multiply each term. So that's going to be I squared times sine A sine B, and I squared is -1. So what actually happens is this positive becomes a negative. So what we just have is a minus sine A and then sine B. So what we have essentially done is just found each Euler expansion for the exponents and then multiplied out the brackets. So what we see here, now let's actually group the real and the imaginary parts together, and I'll factor out the I because we know that they're in more than one term. So what we have here is, let's just write this all in one color now. We have cosine A times cosine B, so that's the first real part. So I'll do it like this. So this is going to be the real parts, like so, and these are the imaginary parts. So I'll do everything like that. So we are now taking cosine A cosine B minus sine A sine B, and then we now add, and then we have an I factored out of that. So we have an I multiplied by sine A cosine B plus, and then we have the factoring out the I here, we have cosine A sine B. So here we are essentially done, because if we refer back to our original statement here that e to the IA plus b is equal to cosine A plus b plus I sine A plus b, we can very clearly see that the cosine of A plus b is the real part and the sine of A plus b is the imaginary part of the function. And what we see is we can actually apply real and imaginary operations. So taking the real part of this entire expression would just return cosine of A plus b, or strictly speaking, taking the real part of e to the IA plus b would return this. And taking the imaginary part like so would return this part. So what do we need to do to figure out each trigonometric function's summation identity? We need to just take their respective part of the number. So we wanted to find sine of A plus b. We see that sine here is the imaginary part. So what we need to do is we just need to take the imaginary part of this entire expression to figure out sine. And I'll put a note here that sine of A plus b is this imaginary part. Well, we know the imaginary part is the part which contains the I in it. So let's find that out. That means, therefore, sine, we can see that of A plus b is equal to, let's do it like here. To make it very clear, we have sine A cosine b plus, we now have cosine A times sine of b. And this is the proof of the sum identity for sine. And we can get cosine very easily by just seeing that if we just get this expression right here and just get it like so, let's just copy this and bring it here. And what we see is that now we can, let's just move this over like so. We see that here, taking the real part now of this entire expression, will result in the cosine of a plus b, because we saw that that is what we computed earlier. Cosine of a plus b is the real part of this. So therefore, cosine of a plus b, so now this is equal to cosine a multiplied by cosine b minus the sine of a times the sine of b. And that is pretty cool, because you can use the complex numbers to even prove the summation identities from trigonometry. So this is pretty cool, and that was it for today's video. So thank you for watching.